use difference in ellipsoid heights for a difference in orthometric heights in a small project sense, which is a good thing if you have a point of truth at your site. Then you can also localize to that point. The only thing is you have to be aware of legacy data, legacy plans. You have to know what datum the real-time network uses, what adjustment of it, what epoch of that adjustment. We know that about C4G, which is a blessing. A lot of states, a lot of networks, we don't know that. I was talking with Dave Newcomer at the break. In Florida, their DOT uses a certain epoch of their, all right off the data sheet for their information, and they're using current positions as if they're published positions, which isn't true, which means the error gets shifted into the atmospheric modeling. So just to say, it behooves us to know what we're using as truth. If that real-time network is supposedly aligned to the National Spatial Reference System, we have to make sure what adjustment of those datum it is using. So we have a lot of plans that are legacy. We have a lot of leveling that's legacy. It makes it a little bit tough, but we have to deal with it. So static or real time? Well, of course, static is a lot more, not a lot more accurate, but it is more accurate than real-time positioning. It's more adjustable. You can process the data a number of different ways. You have longer occupations so that you can deal with cyclical multipath. You can try different cutoff angles. You can do different things with static data you can't do with real-time. But real-time has certain advantages, of course. The company I work part-time for now, GW Stevens, uses real-time a lot. They actually have, an R10 rover. And they'll go out to a site and they'll lock into the network. We have a network that actually runs through 12 states on the East Coast. And they'll use that network for their site control. They're out there in southern Maryland, near the woods, dealing with projects of hundreds of acres, possibly for the state, possibly for a private owner. And frankly, they don't care. They don't care if they're off a tenth or two with their site control, because everything from there on is relative to those points, using more precise methods. But you have to know the accuracy needs of what you're doing before you decide what tool you're going to use. Static takes longer. You have to have somebody that can post-process the data. If you use OPUS, Online Positioning User Service, what do you get? You get 1 point. You don't get any network adjustment, right? So each point is an isolated point position, which is okay, but it's not as good as a multi-session adjustment. OPUS projects will give you a network adjustment, but of course that has its own set of criteria. You have to take training. You have to have the ability to have tiered access and authority. So it has a number of things that you're going to have to play with in order to use that. Real time's kind of neat. You go out there with a rover and it's easy to get data. It's also easy to get the wrong data. So you have to have a practitioner out in the field that knows how to use real-time conditions to the best advantage. We'll try to cover some of them. One thing we've seen with real-time networks, of course, it's harder to get orthometric heights from a real-time network. Generally on the East Coast, Maryland, down to Georgia, up to Maine, along that area, most real-time networks will give you great horizontal positions, but the orthometric heights can be between 1/10.5 to 2/10 inaccurate. So it's something that we do a lot of localization with. They might localize to local control. We have the good fortune to have relatively stable local control. In some areas there's some subsidence, not nearly as much of course as here. But we can localize to benchmarks or localize to horizontal points or both. So that's something we can do easily with real time and look at our residuals. So there's tools for either one. NGS has guidelines for GNSS derived heights that are getting a little bit long in the tooth, a little bit long in the tooth. They were developed in the 90s. Actually, when I was working with Baltimore County government, we partnered with NGS to help develop those guidelines, and that was in the 90s. Since then, of course, real-time networks have come along. Real-time positioning has matured, and I don't know, I feel that you can achieve 2-centimeter accuracy locally with real-time probably a lot easier than using the guidelines. That being said, for large projects, countywide HTMOD projects, you're going to be under contract to do certain things. They'll want to use the NGS guidelines. They'll want to blue book the data and get it into the national database. By the way, that's a neat thing about America. This is the only country in the world where each one of us can submit data and put it into the national database. Pretty cool. And yeah, it's blue booking and it's like a stick in the eye, you're right. But it's still something that goes back legacy-wise, you know, decades and decades. Everything is kind of the same, good database. And, you know, I think that it'll be merged eventually with other databases like OPUS-DB. Anyway, let's talk about OPUS a little bit. Again, I said OPUS is a point position. There's OPUS static. There's OPUS rapid static. There's OPUS net. There's OPUS database. There's OPUS projects. And there's no OPUS GIS yet, or OPUS L1. Probably never will be. But anyway, we're going to talk mainly about OPUS static and OPUS rapid static. OPUS static requires at least 2 hours of data. Okay? OPUS rapid static needs about 15 minutes up to 2 hours of data. There are 2 different programs, and I'll show you how it's kind of neat. If you convert to RINEX, you can actually submit the same occupation to both of them. And you can break it into segments and do things like that. I think it's worthwhile sometimes. We can look at some of the results. Another thing to remember, this is not gospel. When you get a point from OPUS and it says orthometric height and gives you a value, and I think here I'm preaching to the choir, but don't figure, well, that's good, you know, because it may be 5 centimeters, it may be 3 centimeters, it may be 10 centimeters, it may be more than that. It depends. So one thing you'll hear said this afternoon is redundancy. The only way to have confidence with a GNSS derived point is to have redundancy. Okay, and usually it'd be better if you use different satellites to do it. I'm not talking about GLONASS GPS, I'm talking about different kinds, different times of the day when you have different satellites. So we'll talk about that. This kind of complicated picture here is just showing you in the red ellipsoid heights, in the blue horizontal position. This is time in hours, and this is the standard deviation in centimeters, okay? Now, how come we have this line here going from A prime to D prime and all that sort of thing? Well, this is about 15 minutes worth of data. If you look down here, it's somewhere around 15 minutes worth of data. Let's forget the horizontal for now. Just look at the ellipsoid heights. A prime, let's look at that. Where's A prime? Here it is. Ellipsoid height, 3.11 centimeters here. Okay, that looks right. D prime is 5.64 centimeters. Well, what's the difference? The difference is this thing called IDOP, Interpolative Dilution of Precision. It's not like a published thing now, but it's something the NGS is working on as a means to evaluate OPUS rapid static. However, its application really can be applied to a real-time network because OPUS rapid static uses the same thing. It uses up to 9 stations to surround you, wherever you are. Could be 3, could be 9, but it tries to make an umbrella around you and create an adjustment within itself, then an adjustment for where you are. Same thing with a real-time network. So this is actually a tool for real-time networks as well. So anyway, this value, A prime, is based on this particular IDOP value. And the IDOP value takes 2 things into account. It takes the RMS distance to the surrounding stations, in other words, how far apart, how far away they are, and it also takes into account the geometrical position of where you are. So if you're right in the center of these stations, that's the best position because you're going to get an interpolated value that takes all of them equally into account. And you'll get your best position, supposedly. The value for that is simply 1 over the square root of the number of stations. Okay, so 4 stations will be 0.5. We follow that. Then there's an RMS about the distance to these stations. So what Charlie Schwartz and others, Dr. Schwartz and others at NGS have done is come up with a constant to multiply times this geometrical position and a constant to multiply to the distance to these other stations. And they put that together, and of course, as you know, error modeling, it's the sum of the squares, the errors, the square root of that. So he comes up with a value, all right? So these values then are based on an RMS distance of 75 kilometers and a geometrical position of 0.4. Well, that doesn't mean much to us. But what this tells me, and this is twice what the first one is, this tells me that if you have stations that are twice as far away with the geometry that's not as good, you're going to end up with this kind of a difference of 2.5 centimeters. That's all that this graph is telling me. All right, but just take a look at some of the numbers now, all right? So then we move up to about an hour's worth of data. And we're moving here between these two IDOP values, all right? B prime, E prime, so we move between 1.9 centimeters and 3 centimeters. Okay, so for 1 hour of data then, not only have we narrowed the gap between where these stations are, but we've narrowed the gap for the error involved for the ellipsoid height. Okay, now let's move up to 4 hours. Once we reach 2 hours, we can do OPUS static. But let's move up to 4 hours, and we've got C prime, F prime. So now we're here 1.6 and 3. Not too much different than 1 hour. But again, the values are about a little bit better, especially with the further apart stations. Then when you get into OPUS static, what they've always said is, for ellipsoid heights, they came up with another constant, okay? 3.7 divided by the square root of time and hours. All right, well, 4 hours, square root's 2, 2 into 3.7, and you get this value here. And that's the value that it's expected, around 2 centimeters with 4 hours of data for OPUS static. All right, so this is just a little graph they came up with to give you an idea of the accuracy involved. Now, if you notice, it says standard deviation. What's a standard deviation? It's like 68%, isn't it, of confidence? Well, we usually deal with 95% confidence, right, most of the time. That really means you got to double that to get a sense of 95% confidence. So you're going to take all those numbers and double them. So that means with 15 minutes worth of data, you could be looking at 10 centimeters or 6 centimeters for ellipsoid height with OPUS rapid static. Okay, now I can tell you, most of the time it's better than that, at least back in the stable part of the country. So I can't speak for Louisiana, but I can tell you that OPUS rapid static is a very good tool. And here's your criteria for all those different OPI. Is that the plural of OPUS? I don't know. Anyway, OPUS static, at least 2 hours of data. You can go up to 48 hours, but you only cross midnight once. Doesn't like you going across midnight twice. Uses this particular program, Pages. This is what you need, 90%. You got to fix half of them. Here's your overall RMS, your peak to peak. I'll explain peak to peak. Then OPUS rapid static, a different program entirely. 15 minutes to 2 hours. You've got, use half the observations, not 90%. There's a quality indicator, there's a normalized residual. Then OPUS DB, that's the program that goes into a separate database than the Blue Book points right now. However, you're now putting points into the database that you can access. This is the one they would like to see you do for GPS on benchmarks, because it's a great way to submit this data into NGS, goes into the database, can be used to develop geoid models, and it's all done by you. You can set up anywhere, and hopefully when you submit it to OPUS, you come up with these criteria, and you write a little description, you take a couple pictures. You don't have to write a description from the post office in Houma, Louisiana, travel 3 point. You don't do it that way. The pictures tell you about where you are. Then what you do is you get physical ties and write that in the description. 23.9 feet from a telephone pole, you know, on the southeast corner of, that sort of thing. So anyway, OPUS-DB, submit to NGS, and you can then develop GPS on benchmarks very easily that way. There's a program, OPUS Projects, that you need training to do. NGS has to train you. Dave Newcomer is an authorized trainer in the back there. Matter of fact, most of the NGS state advisors are trainers. Most of the training that I know of is free. And once you do that, you can actually go in and use the project to do network adjustments, which is cool. Then there's another OPUS called OPUS-NET. That uses the same idea as OPUS Rapid Static. It uses a network approach and a network adjustment and a local position interpolation. It uses worldwide points, though. It uses maybe like 10 IGS, International GNSS Service, stations from around the world for the modeling and things like that, maybe 3 core stations. I don't see that accessible readily from the NGS site. Dave, have you ever seen an OPUS-NET accessible at all? No. So this is just something we know about. Well, apparently it's not accessible yet. Oh, this is where I have to access the computer. So anyway, let's just look at a RINEX file here. Can I do this without my glasses? That's the question. All right. I'll step back and then we can go to the next one. All right, this is, I'm not there yet. This is a OPUS solution report. Now, what is it? OPUS static, OPUS rapid static, what is it? Rapid static. RSGPS means rapid static. You can also tell, well, you know, you can't tell. This is 2 hours worth of data from 6 to 8 o'clock. Here's your antenna. Of course, that's very important. If you give it the wrong antenna name, you're not going to get a good elevation back, I can guarantee you. So you make sure that it's one of the NGS antennas that's been modeled, which they've modeled almost all of them, and make sure you're using the right one. This is going to return the antenna reference point because the height is 0, 0. If you had a mark and you were set up over the mark, you'd enter the height, the HI, to the antenna reference point of your antenna. So anyway, here we've got a result. Now this result is in the old adjustment of NAT 83, CORS 96, EPIC 2002. Here's the ITRF adjustment in the actual time of the submittal. All right, so here's our result. We've got a latitude, longitude, ellipsoid height, orthometric height. These numbers here actually do represent residuals because you can do a least squares adjustment if you have enough stations. OPUS static does not do a least squares adjustment of the observations from the different stations. It does a high-low spread, peak to peak. It doesn't have enough information to do a true GPS adjustment. So OPUS static will use a peak to peak. OPUS rapid static will use a least squares adjustment. So you've got a normalized RMS. What does that mean? Well, it simply means that if you have a value of 1, it is about what you expected. It's exactly what you expected. If it's less than that, your spread was less than you thought. If it's more than that, it was more than you thought. So what we want to see there is 1 or less, and we do have that. We see that it has something called quality indicators. Those are, first number is the network adjustment. So these, however many stations, 1, 2, 3, 4, 5, 6, 7, 8, 9 stations, then made a cell of 9 stations around where you are, and did an adjustment for a certain epoch of time within itself. That adjustment then is reflected by this quality indicator. You want it to be more than 3. Then what it did was do an adjustment to your point. That's this number here. Again, should be more than 3. So we're looking here, we're saying, okay, all right, that's good. We've used 45% of the observations. You're supposed to use 50%. All right, close enough for me. And then these values are telling me, well, it's only a centimeter for the longitude and less than a centimeter for the latitude in that adjustment. So I'm kind of happy with that. The ellipsoid height is 4 centimeters, and the orthometric height is 4.5 centimeters. Now this orthometric height came from where? It didn't come from the monument nearby. It came from the ellipsoid height plus the geoid model, right? So automatically we know we have a 4 centimeter or more error in the ellipsoid height. Then we're using geoid 09, which is correct for this particular adjustment of 983, CORS 96. Use geoid 09, which it did, and it came up with an orthometric height of 160.857 meters. All right, let's look at the next one. Whoops. Now what did I do? I went to the next slide. Sorry. I guess I want to open it. Oh, come on. Sorry. Where's Notepad? There it is. Okay. I'm not sure what we're looking at here, but let's see. All righty, so now what do we have? Well, we've got a page we can't see. I can see it on the screen, but I can't see it here. Let me see if I can drag it over. How's that? Too much? Sorry. How about now? Does that work? That's all right. Okay. Sorry. Yes. Sorry? This? Oh, yeah, full screen. Thank you. Okay. Observation data. I'm sorry. I can see it on the screen. I just can't see it on the projector screen. I promise I'm going to get my glasses after this. That's good enough. Thank you. I still don't see it. Bugger. All right. We're looking at a RINEX file now, is what we're looking at. This is telling us what signals that it used, 7 different signals. This is telling us the interval, 15 seconds. You can see here, this, I don't know if you can understand this or not, but this is 2005, June 25th, 5:47:0 is the time. And then we're looking at, this is telling us the satellites it read, which is those GPS satellites. If it had GLONASS, it'd have an R in front of them. This is just a text file, all right? So this is readily editable, and we can see this is just the information. What else we see here? A 2 meter antenna height. And that's about all we really need to know out of that one. Sorry. Now, give me 15 seconds. I'm going to get my glasses. I apologize. All right, let's look at this one now. Okay, what we've done here simply is decimate this file from 2 hours to about 15 minutes. So what we're going to do then is submit it to Opus Rapid Static. Wait a minute. So this observation here is 5:50 in the evening. And the last observation is 6:06. So we've got 16 minutes worth of data. All I've done is simply windowed it and deleted the rest of the information. So you've got a text file in RINEX format that you can, really the first one should have shown you a 20-second interval, which was an Aztec default. And what you had to do is Opus will not accept a 20-second interval. So you had to delete that data out of the file, which we did first. Then we decimated the file from 2 hours to 15 minutes. All this just windowing and deleting. So now we've got a 16-minute file. And this is the output from that. So we've got a Opus Rapid Static. Here's the antenna. It was an Aztec, one of these jobs, the old Whoppers, if anybody remembers them. And the antenna height 2. Here's the time we used them. All right, we used 91% of the observations. That's good. Quality indicators, well, the network's good, but the local quality indicator is less than 3. So we're wondering about that. However, the normalized residual is only 0.4, so that seems to be pretty good. And then what are our residuals? Well, gosh, they look really good. Because there's 6 millimeters in the latitude and 4 millimeters in the longitude. And then we're back to our 4 centimeters in ellipsoid height and orthometric height. So for now, but this now is in the current adjustment of NAT83. NAT83 2011, EPIC 2010. Now let's see. Okay. That's the one I wanted to look at first. Didn't come up for some reason. I just wanted to show you, this is a, see that 40-second interval and 00, that's a 20-second interval between them. Opus can't deal with that. So if you're in a format that somehow recorded a 20-second interval, no go. All right, let's just go ahead with this. All right, so we're back to an Opus solution report. This particular one, NAT83 cores 96. The ortho height, I can almost read it. Is that 140 or 160? 160.915. And this is the Opus Rapid Static. Boy, these are tough to read. That's all right. Now up further, Randy. Keep going. We're close. Oh, yeah, that's it. Ah, much better. Thank you. 160.915. This is Pages static. I mean Opus static using the Pages engine, and this is 2 hours worth of data in the 83 EPIC 2002. And the orthometric height is 160.915. This is Opus Rapid Static. Same 2 hours of data, different program, 160.857. Well, That's about almost 6 centimeters difference between the two, right? But guess what? According to the published value, the little short session of 16 minutes actually, oh well, the OPUS rapid static for this particular session of 2 hours came up a lot better. It came, now this is in feet, not meters anymore, okay? So you've got an error of 700ths north, 600ths east, and 1600ths in the ellipsoid height. In the OPUS rapid static, you've got 200ths north, 500ths east, and only 200ths in the ellipsoid height error. Okay, so this, what's the point of all this? 2 points. Number one, you can convert your files to RINEX files where you can edit them with text, as text, with a text editor, Notepad, or whatever. Make sure you don't get any more extra carriage returns or anything like that in that. But you can edit your files. If you have a 4-hour file, you can chop it into sections. You can submit those sections to OPUS rapid static. Or if you have 2 hours or less, you can submit them to both of them. And the reason, the second point being, the reason to do that is because you get better answers with one than the other. Why is that? Well, probably in this case because instead of 3 baselines being averaged, as you would with OPUS static, you've got a network solution that's interpolating conditions to the rover, just like you would with a real-time network. So because you're doing that in this case, you're getting a better answer. You don't always get a better answer, but I guess the point being, use both tools. You can use both tools with your data. Yeah, I've got 4 hours of data, I can't do OPUS rapid static. Well, you can. Just chop it in half, and you could do 2-hour sessions to OPUS rapid static. And I can tell you something else if we don't cover it here. Let's see if we do. I think we do. All right. 83, 2011 adjustment, Epic 2010. Let's see, pages, static, the static, OPUS static adjustment, 2 hours of data, 1641.577. The reason I wrote that in there is because in this case, GeoID 12 wasn't available. And the data was done in 2012. But anyway, if you apply the ellipsoid height in the GeoID model, 12A, you would get 1641.577. And when you chop data up, you can see that this is OPUS static the first 4 hours. This is OPUS static the second 4 hours. You've got 2 centimeters difference between those 2 chops. The first 4 hours gives you one answer, the second 4 hours gives you another answer, and they differ by 2 centimeters. So what you'll be getting by doing all this way is a coupla, C-O-U-P-L-A, couple of centimeters, and that's what you'll be batting around. Same thing here, OPUS rapid static the first hour, OPUS rapid static the last hour, +8 and -9 millimeters, almost 2 centimeters there. What's the point? The point is redundancy. The point is checking with different programs if it's an important point. If you don't need accuracies better than a couple centimeters or more, even horizontally, it's not a big deal. If you're trying to get the best to start with, then it doesn't hurt to submit this to NGS in different ways. Now, also, one more thing, one more point. This data is from a core station, because it's easy to get the data, right? You get it anytime. That's a perfect scenario. There's usually no multipath to speak of, at least not bad multipath. You've got an completely open sky, right? You've got it somewhere that's supposedly halfway stable. This is more or less the best site you're going to get. And we've got a couple of centimeters variation in one solution. So at your site, on your setup, with your observation, probably not going to be as good a condition. So this is the best you're going to get. So I just want you to be aware of that. This is different days. This is day 69 and day 335. Not that that's a big deal, but here's a couple centimeters here between them, between OPUS static and OPUS rapid static. Difference between those two processing engines gives you a couple centimeters different. Here's the difference between 1 hour of data using OPUS rapid static and 1 hour of data using OPUS rapid static on a different day. That difference by 2 centimeters. So you can see everything that you're comparing here is a couple of centimeters different. Whether it's the same file, a different file, 2 different programs, just be aware that what you're getting is not gospel. It changes according to what the conditions are and according to how you're processing it. Here's another, actually, a way to check OPUS rapid static available at the NGS website at this address. And you can go there, type in any point or pick any point. It'll give you 1 sigma, 68% confidence, errors, either for the horizontal or for the ellipsoid height based on different times. It could be 15 minutes, or excuse me, OPUS rapid static for 15 minutes or 1 hour. And it'll give you, and again, it's hard to read, but again, it'll give you a difference here and a difference here, 3.5 centimeters, I think it says, for ellipsoid height. That's easier to read. So this is 15 minutes worth of data, and it tells you roughly to expect a 1 sigma ellipsoid height error of 3.7 centimeters. That means 7.4 centimeters for 95% confidence. That's a lot, but that's what you could expect at that point from OPUS rapid static. Usually it's better than that. This is 1 hour of data at the same point. It drops down to 2.2, so 4.4. A lot better with 1 hour, isn't it? And that's true with OPUS. The single best thing you can do with OPUS is have more data, longer session. That's the single best thing you can do. But anyway, this tool will tell you the approximate expected error at any point using OPUS rapid static. Okay, there's another point, and that is the horizontal. And the horizontal you can see is much better, 1 centimeter. And I'm not going to suggest this to do all the time, but if you've got a super important point, just like we were talking about getting an ellipsoid height du jour at the RTN stations, you can look at this plot. And let's say you were at station for day 170. You could go up here and say, oh, well, here's the published value, and this particular day, this station was 3.5 centimeters higher than that. So you could actually adjust that baseline, if you were to process it, by 3.5 centimeters for the ellipsoid height. So this is just another way, another tool maybe to tweak your solution. Obviously, we're not going to do that for every point, but it's something, again, that could be built in to a real-time network. Here's a picture of what you would look at after a OPUS DB submittal. And you'll have pictures of the point, you'll have a latitude, longitude, an XYZ. Well, we know what that is now. That's an XYZ from the origin of 983. And, you know, the geoid model, the epoch, the adjustment, point scale, combined factor, the typical things you would expect to see on a data sheet, only just a much friendlier look to it, isn't it? And this, again, is in a different database than the NGS integrated database, which is all the millions of points that have been put in by Blue Booking. Here's another picture. Really nice tool. I'm not going to talk much about OPUS projects. You need training to have access to it. However, it's a network adjustment. It's not a point position like OPUS static, OPUS rapid static, OPUS net, OPUS database. They're all point positions. This is a network adjustment. You could develop a huge project with this. You could do a county or whatever, a state. And what you would do is you just go out and get some data, and as project manager or whoever has access to get in, Submit the data to this project. You can name a project, submit the data, and Dave, please tell me if I misspeak, okay? You submit the data, and don't finalize it. You go out the next day, get more data, submit that. You go out next week, get more data, submit that. Then when you're done, you hit the magic button, and it does a network adjustment. And you've got the equivalent of what you might get using the manufacturer's software yourself. It's a great thing. I think it's a great tool. I think it's maturing. Some people say it's a little clunky now, but I think that it'll mature. I think more people will be using it, and hopefully one day you'll just be able to read about it without taking the training. OPUS-Net, again, just using global stations as well as local cores. Not accessible yet, but what it does do is perform a network adjustment, like OPUS-RS. Okay, now, static work using NGS 58 and 59. 58 is GNSS, GPS-derived ellipsoid heights, no GLONASS. GPS-derived ellipsoid heights, 59 is GPS-derived orthometric heights. Do you do the ellipsoid height, do the ellipsoid heights first, then you do the orthometric heights. It's worth looking at, okay? But you wouldn't use this for a bridge job out in the middle of the country. You use this for a big pipeline or, a county-wide HTMOD network. I've done 2 of them, one in Fairfax County, Virginia. I'll just show you some slides, or a couple little slides of it, and graphically. So it works well. Here's the theory. The theory is this. Use these guidelines to produce either 2 centimeter or 5 centimeter GPS-derived orthometric heights. Can you do it another way? Yeah, probably. But what NGS is saying is, if you follow these guidelines, you will get 2 centimeter local accuracy in GPS-derived heights. So, and it's true, you will. It's a lot of work, though, I can tell you. Okay, so 158, 59. Now here's the update study I was talking about from South Carolina. They're actually using real-time positioning, too. And they're trying to see how reliable they can do this to produce maybe comparable GPS-derived heights. I don't mean to complain, but I wish they would have talked to me too about this. I think I could have helped them. Anyway, network local accuracy. We're talking about 2 centimeter local accuracy. That simply means point to point in your campaign, your leveling or your HTMOD campaign. 5 centimeter to the national datum. Okay, that's what we're talking about here. Here's the theory. Start out with the best control you can. Well, it used to be HARN, High Accuracy Reference Network, monuments in the ground. I guess they're still around, but of course the source of truth is really the cores network for NAT83. So you start out with the cores, you go down to the next best control you have, you go down to primary base stations you may have had to set. When do you have to set this stuff? You set it when your spacing tells you to. If you have HARN 75 kilometers apart, you're done. Your primary base stations, you're talking about 40 kilometers apart. That's a long way, 24 miles. Then you go down to secondary base if you need it, 15 kilometers apart or 9 miles apart. Then you go down to your local network where you really want to be to begin with. You want to have no more than 10 kilometers between them, and you want to average 7 kilometers between them. So you're going to have some close, some no more than 10. That's what you're trying to do. Start out with the best, work down in steps, if you have to the local. Now, in Baltimore County, we didn't have to do HARN. We did HARN, but we didn't have to do primary base or secondary base because the HARN was close enough we could use them and go right to local from there. So the only way you want to make sure you have this kind of spacing, if you have 40 kilometers, that's your primary control. So you just start out and work down towards your project. That's the theory. Here's Fairfax County, Virginia. I'll try to click this again. So 145 stations. This is Washington, D.C. up here, and the Potomac River is down here, and adjoining counties here, Loudoun, and they had a network that they were cursed and blessed. They had an early GPS work done back in the early 90s. The bad thing is it was only done like to around second order accuracies. So they had a lot of kind of bad data, and then their elevations were 29 based, and we wanted to upgrade them to 88. So we did a HTMOD network. This was under contract when I was working with a private firm, actually the same one I'm with now. And so we did this. And the thing is, you have to observe these baselines redundantly, so you have to do them twice. You have to have them spaced in time by 4 hours. So you can't just set up and turn it off and turn it back on again. You have to have a spacing of 4 hours so you get different satellites overhead. You also have to observe the closest neighbor. So you can see there's a little bit involved here with planning. Think of the logistics of something like this. We did 6 receivers, so we had 6 trucks, 6 people having problems all the time. And every day, I was out with them, but they would find a different way of screwing up. They were really creative. I mean, it was amazing. Unfortunately, when I was with Baltimore County, we had fixed height poles. They were 2 meters. They weren't collapsible. They were 2 meters. That means if you had a car that stuck out the window of the car. These were collapsible fixed height tripods, which means they had a dowel that went through the different heights. So you had 1.5, 1.8, and 2.0 meters. Of course, everybody had 2.0 meters all the time, even when they used 1.8 or 1.5. And you think that doesn't drive you crazy. And then somebody would break down, and then somebody's cable would break, and then they couldn't find the point, and they set up on the wrong point. And just imagine anything you can. This is why I like real time. Anyway, so all these are observed redundantly. They're observed with 4 hours staggering in time, or the next day at a different time, so when you have different satellites, or whenever, a week later, whatever it is. And that's what we did. We had to design a network that sort of went like this, and then we went back around like this. But it had to hit at different times. So it took a lot of planning. I mean, that's a lot of the logistics. And we had something like this. God help me, here we go. Sorry. This will work. This is a Pentium 1. There it is. Can't see it, but there it is. Let's blow it up. So this is just like a typical observation schedule. Okay, can you see that all right? No. Let's go bigger. I can see it. Come on. All right. You don't really need to see all of this. But you can see this is the plan. Every day, that was the plan. Observe time. Observe here. Everybody had to have a map. Everybody had to know where they were going to go. I'm sorry. No, I don't want to check online. Thank you. And that was an observation schedule. Let's go back. Don't. All right, so what you need to do is this. Again, this is worthwhile for a big area, a county, a state, a HTMOD project that covers a long area, a pipeline, anything like that. You're not allowed to make blunders, obviously, like we did. Dual frequency receivers, geodetic antennas, that's a given. Fixed height tripods. Your primary control, you start out with 5-hour sessions on those babies, and redundantly, and then you process them against themselves first. Then the local ones, when you get down to them, you can get away with 30 minutes. We did 45. The idea is to stagger the or to occupy the benchmarks, validate them to see which ones work, but have them no more than 20 kilometers apart. Sometimes easy, sometimes not easy. Not too easy here, I don't think. The baselines, I said, had to average 7. Then there's a position dilution or precision we'll talk about, but the value is 4. If we had to do that today, I would want 2. And pictures and things like that. So you need to do that in the field. If there's a wonderful benchmark, which is here, set in bedrock, we want to use that, but we can't occupy it for GPS. So you set an eccentric point over here somewhere where you can have open sky, and then do an elevation transfer by good procedures to that point. And then you have transferred that excellent NAVD88 orthometric to an eccentric point. When we did Baltimore County, the first area on the east side of the county was done by a contractor. I was working for the government. And they set PK nails for eccentric points to good benchmarks they couldn't occupy. Those PK nails are in the national database now. They got blue booked. So we have 2 PK nails in Baltimore County that are blue booked. Just interesting. There's the control. However, they didn't work together real well. And actually, this one was bad, so we had a big blank area here. This is Dulles Airport here. And there were problems. And the county, Fairfax County, actually did geodetic leveling, what they called geodetic leveling, without any procedures. And we used some of those verticals. Okay, so when you process, these guidelines say if you have any baseline that's longer than 5 kilometers, you're not going to use what they call the L1 solution. It's usually the one that's there, the best. Use what they call the iono-free or L3 solution. That uses, I think we'll cover it, but let's just say it uses modeling to model the conditions through the atmosphere that takes out the first order ionospheric air. So anyway, use that solution for anything more than 5 kilometers. Well, that's kind of overkill to me. I would say 10 kilometers or more. Then you do a minimally constrained adjustment. Then you know, constraining 1 point. Then you do a fully constrained adjustment, adding the known stations that have worked. The goal is 2 centimeters. The processing, this is the tough part, because if you have a GIS manager, no offense, Josh, that wants you to occupy a point underneath a tree for a flight line, and it's an oak tree, and he wants that point occupied, you're going to have a lot of problems getting an RMS less than 1.5 centimeters. And sometimes that happens. Also, every time you do the redundant baselines, you've got to have them repeat to within 2 centimeters. So this is your goal. If you do that, you'll come up with your answer, the right answer. You're going to have a cutoff angle of 15 degrees. So you don't get the noisy data coming through the atmosphere, and the processing, but you're actually going to collect the data to 10 degrees, which I agree with that. And the thing here is, if you remember what I was saying before lunch, the ephemerides of the satellites that tell you where they are exactly. The post-fit tells you where they really were. The broadcast is what they send you. And what these guidelines say is wait till you get the precise. Well, really, pragmatically now, you can use the rapid orbits, which you can get 14 hours later, 10 hours later. And they're almost just as good. So again, these guidelines, at that time, that was correct, because I saw a lot of differences between broadcasting. What you do is an error check after each day. You process the data and there's no blunders. Okay. Then, later when you get the precise, you reprocess and get a final answer. So this is the guidelines. Also, just process the non-trivial vectors or independent vectors, whatever you want to call it. The theory is that when you have a setup, for instance, with five receivers, that you can have 10 possible baselines. And if you look at this little formula here, 5 times 5 minus 1 divided by 2, 10. But the real number of independent baselines is 4. The rest of them are inverses. That's what's considered. I've heard people say, no, they're all fine. Well, the only bad thing about doing all of them is that you're going to get a better statistic than you really should be looking at. However, the good thing about this is if you have a problem with this baseline, you can't get it to agree within 2 centimeters, you can't get the RMS down to 1.5, don't use it. You can use another baseline. Use this baseline instead. You don't have to use any particular 4 baselines. So if you've got one that doesn't work, don't use it. That's a good thing. Can you get the idea that this takes a lot of work in the office? Yes, it does. Baseline processing, TGO, TBC, that's what we were using. We weren't using TBC, obviously. I just want to show you how the reporting has changed. By the way, standard error of unit weight, it's just the a posteriori errors compared to the a priori errors. In other words, what happened versus what you expected to happen. If you have a 1, it means they're exactly what you expected. Less than that, they're better. More than 1, they're worse. The reference variance that you look at is just the square of that value, kind of like a covariance, all right? And the ratio, again, is the best to next best. The root mean square is the spread. That's all. Not to belabor the point, but this is what we got when we were processing the data. I think this is telling me I need to click here. Okay, so just to stay here a second, this is telling you what solution it used. The iono-free fixed because the baseline was more than 5 kilometers. It was 6.7 kilometers. This is a baseline processing report, okay? Tells you the cutoff angle. The reference variance was 2.02. Well, let's see, the square root of 2 is 1.4. So that tells me that standard error was about 1.3 or 4. So it was a little bit more than I thought it was going to be. RMS, we'd like to see that a little bit better than that. But anyway, this is what you're looking at, okay? So then it gives you the baseline components. It gives you the northing, the latitude, the height, standard errors. You want to look at that, and the covariance, et cetera, et cetera, et cetera. Then it gives you this information about what it used. This is what it used. These are the different satellites: 2, 4, 5, 6, 10, 13, 26, 29, 30. Now, if you look at this is L1, L2 frequencies. You can see there's a lot of cycle slips here, and there's no L2. Down here, kind of the same thing. If I was to reprocess this, I would dump satellite 13 because it just isn't worth it, and I'd cut off the data here. This is what you can do with static positioning and reprocess. Can't do that with real time. So let's go down further. Okay, this is the other point. This is the one underneath the tree. Can you see there's a lot more cycle slips and everything else? It's much noisier. Looks horrible, really. But actually, Trimble came up with an answer. We saw what the answer was. And it wasn't so bad. This is what Trimble said, or TGO said. The shaded area is what it used. Needed at least 4 satellites for static work, 5 for real time. And you can see what it did. So at any particular point, you've got 4 satellites. All right, enough of that. And then I just wanted to show that the newer software, and I'm not familiar with Leica Geodetic Office, used it years and years ago. Bob Lemoyne taught it down in Corbin, but have not had access to it. I'd love to, but I don't. Or TopCon or the others. Oh, that's right. Sir? Yeah, thank you. So this is what then you look at with the newer software. You don't see any reference variance, do you? So they've taken that out. It tells you it's a broadcast orbit, so we know that's not the best orbit, but hey. The maximum PDOP, which is nice, so 2.5, that's okay. The vertical precision, the horizontal precision, processing interval, the duration was 38 minutes, and then kind of the same information. This is all stuff, though, that you can do with static positioning. And this is the, if you notice here, we've got some R's, the GLONASS constellations here. And when the satellites and the data looks pretty nice here, except for this guy, this GPS satellite 14. That doesn't look so good. But see what you can do post-campaign, you can do all this. And here's the spread of the residuals, the plot of the residuals. This one looks real good. That one looks real good. So you can look at all this. Let's get down to some GLONASS satellites. Where are they? Here's one. That looks good. That's a little noisy, not too bad. That one's pretty noisy. Now there's one I might knock out if I was going to reprocess. And you could, it's not hard. You just say, just highlight it and it'll blank it out, reprocess, get another answer. That's what's nice about processing the data. It's not hard once you get in there and get it in there. So that is what we're doing with the guidelines for static. Well, we know why RMS is squares. We don't need to do that one. Static, this is what you can do. You can't do with real time. You can use other redundant baselines. We talked about that. You can, well, we talked about using other baselines. What I meant by other redundant baselines is some sessions you're going to have 3 or 4 baselines for the same 2 points. And you're going to look at all 4 of them, and you might see that 3 of them agree and 1 doesn't. You're not going to use the one that doesn't agree. Or maybe these 2 agree really well, and the other 2 maybe not so well. Well, you only need 1 redundant occupation. So you're going to pick and choose which 2 work the best. Using the statistics. Doesn't mean you're going to pick the 2 that are closest and they're wrong. You're going to look at the statistics and pick the 2 best ones. You can do that. You can change the cutoff angle. That's another thing I didn't mention. So instead of processing it at 12 degrees or 15, you can raise it to 20 and process again. You're eliminating more data though, aren't you? So you don't want to raise it too high or you don't have enough data and you're even if it processes it, you know, your statistics will be inflated. You don't want to trust that too much. So you want to keep it much, well, not above 25 degrees, I would say. Anyway, things you can do. We looked at editing the satellite data. Yeah, you can always reobserve. So here's the adjustment summary. So over here is the ellipsoid height error. This is where we were after 1.5 centimeters. And we've got it for the most part. Now here's an outlier, 24 millimeters, you know. When you do a project this big, you got to live with a couple outliers. I'm sorry, but you do. Especially when they make you set up underneath trees. Chi-square is just another statistic to look at. It doesn't, because it fails a chi-square test doesn't mean it's bad. It could look too good, and it would still fail a chi-square test. It just again, it compares the a posteriori to the a priori, but with a number of redundant observations. Okay, so I'm not going to belabor this. You do an adjustment constraining 1 point and 1 orthometric height. You've already done the ellipsoid height adjustment. Now you're going to do the orthometric height adjustment. Constrain 1 point, add 1 elevation, do the adjustment. What happens? How do they compare? Apply the geoid model. Do you have any outliers? Hopefully not. Then you look at the difference between the GPS derived with the published. This is that same Fairfax project. It wasn't the best in the world, but we did pretty well. There's a couple outliers here. Here's one that's 4 centimeters. That's actually a horn. So then you say, well, which ones are valid? Well, they should all be valid, but more or less what NGS is saying is get rid of the ones that don't agree. And you're not going to do this work for 5 centimeters, believe me. You're going to do this for 2 centimeters. And there may be some systematic errors or tilt involved. So then you do a full, once you have looked at all that, you've gotten the outliers out, then you start to add the known benchmarks to this and do an adjustment, least squares adjustment. Don't add them all at once, because then you won't know where the outlier is. Add 2, and then do an adjustment. Doesn't take, all you gotta do is hit the button once and look at the results. Okay, add 2 more, all right? Add 2 more. Whoa, something happened. So then you can go back and look at it. All right, guys. Okay, so add them a couple at a time. Ensure that they do not distort the horizontal adjustment when you add them. Okay, the horizontal will follow this, just automatically. Okay, so this is more or less the adjustment statistics. Reference factor was 1. That's really good. The redundancy number, a lot of redundancy, degrees of freedom, past the chi-squared, redundancy number, blah, blah, blah. Now what it has done, here's the adjusted elevations. Okay, this is where we were going for 2 centimeters, right? I know it's hard to read. I'm sorry, I'm using the wrong pointer again. I know it's hard to read, but here's one that's 2.5 centimeters. These are all okay. Here's 21 millimeters, 23 millimeters, 22 millimeters. To me, that's Miller time, I don't know. But what happens in the adjustment is, if you recall the ellipsoid heights in the screen I had up here, the ellipsoid heights were like less than 1.5 centimeters. So what it's done is it's changed all the ellipsoid heights to match the benchmarks in the ground values. You've got that h equals little h minus n going on. You're holding the n, you're holding the big H, and you're changing the little h now, because nobody uses ellipsoid heights. So all these ellipsoid heights now have been changed. They're 4 centimeters, 3 centimeters, 4 centimeters, because we've constrained the NAVD88 values. They don't all agree, do they, when you plug them in that little formula? And that's the way it is. There's the comparison between the ellipsoid before and after the orthometric adjustment. I don't know if you can see it all, but again, it's 1.5 to 4. That's how it changed. Okay, so the theory is constrain the marks in the ground, published, new control, ellipsoid heights, the geoid separation, you'll get a GPS-derived height. Hold the published elevations, hold the geoid separation, change the ellipsoid height. That's how they do it. And this is what you get. You get a mark that says it's identified as a HTMOD station. You get a GPS OBS as the adjusted to the nearest centimeter. You get a statement about it, how it was derived by GPS and a geoid model. Okay, so that was a summary of the static using, say, Fairfax County as an example. How about if they did something like this and put in 6 real-time stations, just 6. Every time they fly that for updating their orthometric heights photogrammically, they go out and panel known marks. They go out after the flight, post-flight ID points on corners of walks. They do all this. You can do all that with a real-time network. You don't need to do that every time you fly. These are all the flight lines, by the way. And we had to be along those flight lines for a lot of the points. So you evaluate the geoid. This is similar to what we're talking about down here. Build a quasi-geoid. You do the truth of NAVD 88 instead of in Fairfax County on the RTN stations here at C4G. And then you know, the stations have been constructed here. You have coordinates on them. You do an adjustment of them, it's been done. You do the evaluation, and of course then you create a real-time network like we have here. But the key there is, what is truth? Is truth what's published for NAVD 88, or is it somehow related to our ellipsoid heights and a geoid separation? It should be, but how do we want to approach it? Okay. Now, heights from real time. Oh, we're going to 245, aren't we? 15 minutes. I'm going to go rapidly. Am I right? 2:30 now? I'm going to go rapidly through the beginning of this so I can get to the best methods if nobody has an objection. Two sets of guidelines for single base and for networks. The networks is still a draft document. However, they're both available at the NGS website. The links will be available after session. One thing I'd like to show is this slide, the native condition of GPS signal. If you're on the Earth and the Earth is rotating, you're going in this area about 800 miles an hour. And the satellites are overhead and they're going about 8,400 miles an hour in different directions. So what you've got to do is you've got to decide how many cycles along that frequency came down from the satellite to my antenna. An integer number of cycles. You've heard of ambiguity resolution. It's an ambiguous number of cycles that you have to figure out. It's not time tagged like the code is. We don't know how many cycles are there. We know a partial cycle when it locks on, but that's all we know. So that's what has to be done with real-time positioning, ambiguity resolution. That means each satellite on each frequency will have an integer number of cycles for each frequency between it and the antenna where you are. What is the solution? It has to be a least squares solution of somehow it has to come up with this count of cycles. The trouble is, this is not even with anything affecting the signal, but the speed of the satellites. Relativity comes into effect. Thank you, Dr. Einstein. Special relativity says because those satellites are going so fast away from us, or in different directions, their clocks appear to run slower to us. So we've got to correct that. We've got to add 7 microseconds to them so that they run at our speed. But because they're so far apart from us also, they're less affected by gravity. So general relativity says their clocks run faster than us because they're less affected by gravity. So we've got to take 45.9 microseconds away from them. So if you add those two together, you've got to take off 38 microseconds from the clocks of the satellites. And those clocks are atomic clocks in the satellites. They're very, very, very accurate. Because 1 nanosecond, 1 billionth of a second, coming down to us is a foot in range. You know, we need to know stuff better than that. So we're talking heavy-duty stuff. Anyway, so that's what they do. They adjust the clocks of the satellites before they launch them by 38 microseconds. It's, to me, that's fascinating. And, so then you have to decide which one of those integer counts is right. This is the situation. You know this. I'm sorry, using the wrong pointer again. You know this partial cycle when it locks on. You don't know this. So we have to decide that. We have to get our errors down so that we can resolve this to 19 centimeters. So we can figure out what cycle, how many cycles that is on L1. All right, real-time positioning. This is just some of the stuff you have to know. Not unlike static positioning where you just hit the button and turn it on and hit the button and turn it off. The practitioner has to be the one with the expertise in the field. That's probably known by everybody, but there's a lot of stuff you got to know. We know the advantages. 3 possible scenarios: single base, right, with a UHF radio, with a modem, a user base station with a modem, or a network operated for instance, in Louisiana. What you're looking for is this, of course. This is the best scenario. You want more satellites, shorter baselines, low dilution of precision, open sky, low RMS you're looking at, continuous communication, blah, blah, blah. We don't always get that, do we? Just to know that we start off with the satellites in XYZ, not in the NAT83 datum, but really WGS84 datum, which is close to IGS, and you end up with state plane. This is strictly a mathematical conversion. There's no error to get to state plane. When we add the geoid separation is where we get the error to the elevation. But until you go from XYZ to the state plane north and east, there's no error. It's just a mathematical conversion. A float solution. If you're out with real-time positioning and you look at your data collector, and well, this doesn't happen a lot anymore maybe, but it used to say float, and it would say maybe like 2 foot horizontal position, or RMS. And it would go down, 1.5, 1.0, and all of a sudden it would say fixed, and it would go down to a centimeter or 2. That's what this is. That's your receiver trying to figure out how many of those cycles are coming down from the satellite. Ambiguity resolution. Until it does, it has a bunch of decimal counts. So it doesn't have a fixed number. It has like 0.223, 0.577, 0.993, and it doesn't always round them the way you think it would. That's a float solution. That's what you're looking at in your collector when it says float. Of course, we don't want to locate anything important with a float solution. This is the single base guidelines. You want to be concerned with Chapter 5, which is field procedures with a table. Chapter 8, which is a summary. If you want to read the rest, that's fine. A glossary. This is from Chapter 5. It's sort of a summary table of 4 different precisions. And all it is telling you certain criteria to achieve a certain precision. Centimeter and a half horizontal, 2.5 centimeters vertical at 95%. If you do this, have 2 locations from different base stations, PDOP less than 2, an RMS of 0.01 meters or 1 centimeter, blah, blah, blah. Down here, it's more of a GIS accuracy, because you're talking about a decimeter and a half horizontal, 2.5 vertical. So this is recommended criteria to achieve a certain accuracy between the 2. Again, can you do it somewhere else? Yeah, of course. But we're saying if you do that, you will achieve that particular precision. These are things that affect the signal. Adds up to what? What do we get? 3 meters, 5 meters, walking around? Something like that. That's our errors added up. Very, very quickly, this is just a cookbook summary of all the errors. And these particular criteria with the orbit, the ionosphere, the troposphere, they all add up to parts per million error. The theory is the further you go away from a base station, the more chance you have of not being in the same condition as the base station. So your error model is now wrong or not as good as it should be. Okay, the upper part of the atmosphere, the ionosphere, can knock out your communication. It can give you noisy data. It can prevent you from getting a fixed solution. It can prevent you from working. We just supposedly went over a peak in that activity counted by sunspots. And it really was kind of benign. But that really can happen at any time, worse during the early afternoon, worse at the equator, but you get other stuff going on near the pole. You can also get charging on the satellites, and that can affect the data as well. The ionospheric error, when you have a period of high activity, can give you up to 14 centimeters of error. In a benign time, it's about 2 centimeters. So you can see it makes a difference what's happening up there. With a network, you can model it, so you can go out to 30 kilometers and get better information than you can with 10 kilometers single base. Another advantage of a real-time network. Some ways to decide the ambiguity resolution and to eliminate the ionospheric error. We don't need to talk about that right now since we're running out of time. Those are the equations for that. The troposphere is our weather. The dry part of it's easy to model. The wet part of it's hard to model. The recommendation, of course, is don't do real-time work when a storm front's moving across your base station or even across the network stations that it's using while you're in a different weather condition. This is where the theory is 10 kilometers. It says, well, in 10 kilometers, you ought to be about using the same kind of conditions. The 1 part per million gives you 1 centimeter error in 10 kilometers. But if you go more than that, your error starts to add up. That's the part per million. The real-time network can model that error and provide you a solution that you can't get with single base alone. Here's the expected sunspot activity that indicates high ionospheric conditions, coronal mass ejections, and the geomagnetic storms and all that. Place to go to get broadcast information about that is a Space Weather Prediction Center that'll send you reports. Here's one of the reports that you can get, I think. There it is. The index warning that'll tell you when there's storms going on. Orbits of the satellites. Where is the satellite? Broadcast-wise, what it sends you in real time is this red line. It says, here I am. Of course, that's wrong. Could be a meter wrong. Could be 3 meters wrong. This is where the satellite really was, this green line. And this is what you get as a post-fit orbit. It's fit into that, but you only get it days later. So that's a source of error. 1 to 3 meters, ultra rapid, 2 to 4 centimeters with 6-hour updates. Some RTN can use this kind of orbit information for real time. Rapid orbits, 1 to 2 centimeters, precise, 5 millimeters to 1 centimeter, 10 to 14 days. Rapid orbits are the ways to go for post-processing right now. So the part per million adds up, so you get 4 centimeters at 10 kilometers at 95% 3D. That would match manufacturer spec. Can you do better than that? Yes. But the manufacturers will say for real-time kinematic, 8 millimeters plus 1 part per million. 15 millimeters plus 1 part per million. There's that part per million, your distance involved. That is 1 sigma, 68%. Double it for 95%. Same thing, here's Ashtec, here's Leica. They're all about the same, a centimeter plus a part per million horizontal, 2 plus a part per million vertical. Pretty much the same. Here's that cookbook of summary of all the stuff going into the cycle count. You can eliminate a lot of it by certain mathematical procedures called differencing, which we're not going to carry. Precision and accuracy is worth talking about. When you have single base positioning, your solutions relative to your base station are giving you precision to the base station. If you type in the wrong coordinate for the base station by 100 feet, your data collector will tell you the same precision as if you typed in the right coordinate. So that's the alignment to the base station. The accuracy is how that base station aligns to your truth. Same thing with the real-time network. You're getting precisions of your point from the real-time network. That is your alignment to the network. How the network is aligned to the truth or the national datum, hopefully, is accuracy. So precision and accuracy. Obviously, you can see that a spread of observations or points of observation averages close to the truth. So the RMS is relatively large, precision is poor, but the accuracy is pretty good. This has good precision, but bad accuracy. And of course, this has both good precision and accuracy. So just because you have high RMS, the spread doesn't mean you have a bad answer. Usually indicates not as much confidence because you don't know where in that spread the answer really is. So if you have a tight spread, you say, oh, well, I'm plus or minus 1.5 centimeters, I'm happy. So that's why you look for a low RMS. Okay. Do we all know dilution of precision? It's simply a unitless factor that just tells you about the geometry of the satellites overhead. If they're close together, you're going to get a higher dilution of precision than if they're spread apart, because the intersections give you a larger area than if they're spread apart. Very simply, that's a number that it's a relative factor. The recommendation is 2 or better. And this is just planning. This is just saying that using GLONASS can help you when GPS won't allow you to work with only 4 satellites here. GLONASS will allow you to work with 10 satellites. Same thing here with the dilution of precision with just GPS. With GLONASS, you can work. This is only 3 here. GLONASS uses a frequency-dependent multiple access, frequency division multiple access. So they use a bunch of different frequencies, the same codes. GPS uses a bunch of different codes and the same frequencies. You can do surveying as long as you have 2 GPS. If you have 4 GLONASS, you can do surveying real time. And it'll help you in urban canyons and areas of the highway with trees where you have to get an important point. GLONASS will help you in all those conditions. If you have 7 GPS satellites, you will not get a better answer with GLONASS. But you might be able to get an answer if you don't have 7, where you can't with GPS alone. Multipath can't be modeled out with real-time positioning. You're only there for a few seconds. If you were there for 20 minutes, 30 minutes, like for static positioning, because it's cyclical, it can be modeled pretty well. So you're modeling it out with static, but you can't model it with 3 seconds worth of data. You're hoping that your antenna can reject it because it creates sort of a blurred picture like this at your antenna. You just have to be careful. This is one of the experience factors with real-time positioning. The network guidelines, just the advantages. I think most of us know the advantages. You only need half the equipment to go out and survey. You don't need any base station stuff. Or you get double the production by taking Fred here, and instead of having him sleep and babysit the base station, you give him a rover pole and you've doubled your production. Also, we talked about being able to update to the new datums automatically from the real-time network. Easy. You don't have to recover a point. There's no part per million first-order error. You've taken that out of the equation because all the stuff is modeled and interpolated to where you are. All the error conditions are interpolated to your point. So you've taken that part per million error out of it. Here's the guidelines. I would say that Dr. Snay's chapter on obtaining coordinates is an important chapter. Roughly about 107 stations, real-time networks in the country. When Dr. Neil Weston asked me to do this, it was about 5 years ago. So I don't know how many there are now, but a lot of public networks and a lot of private networks. So basically, the NGS just wants everybody to work within the network with whatever equipment they have using open generic formats like RTCM, which is is what we hope as well. We'll skip the precisions of RTCM. The main thing is, how does the RTN align to what's truth, the National Spatial Reference System? So we have to know that because not all RTNs are created equally. C4G, excellent network. Randy has been cooperating with the NGS all along. He's helped us with our beta model. Well, I shouldn't say us, what used to be us. He's helped the NGS with their beta model. And C4G is very heavily involved with the National Geodetic Survey. Again, RTN give you good horizontal positions, and the vertical is always a question. So if you have site control that's truth, that you're holding as truth, you can calibrate to that, even with 2 points. You can do a vertical calibration and use that. Otherwise, you're reliant on the geoid model. Yes, you have good ellipsoid heights. How good is a geoid model? What we really need is some validation points within the network that we can go out and plunk our rover on, use the network, and see how it compares to what we consider truth. We can do a lot of stuff with the network itself to see if it aligns to the National Spatial Reference System, but all that's no good if you can't go out and get an accurate point in the field. Weight the cores, do an adjustment, and come up with an OPUS value to see the coordinates, do a least squares adjustment. There's no velocities vertically assigned to a station from the NGS, vertically. So you have to develop it after 3 years. Here's that beta tool I was talking about. You can see Randy has given us data here. What you do is you slide over that point, expands it so that you can see all the points in that network. Actually, this is in Washington here. And you can click on them. You can get the difference between the published value and what's used at the real-time network. Hopefully it's within a couple centimeters. And between what's used by the network and an OPUS-DB solution submitted to NGS. All right, here we go. I'm going to take, is it okay if I take 10 minutes? This is really the crux of what I wanted to talk about, the best methods. I can do this in 10 minutes. Can I do it? Thank you. It'll maybe shorten our, well, maybe not. Maybe won't. All right. The 7 C's of NOAA's NGS. Let's talk about what you want to do in the field as far as best methods for real-time positioning. This probably, let's see, as it comes up in color. No, it does not. All right, originally this was blue for single base real-time and red for both network and single base. So you'll just have to look for the B's and RT's at the beginning. All right, check equip. A lot of this is only important for important points, control points, things like that. But let's consider what we have to do. Make sure that your bullseye bubble's adjusted. Make sure your pole's not warped, so that when you adjust the bubble, you actually have a vertical point and not someplace else where you're locating the point. Make sure you have plenty of battery power, especially if you're running a single base, which this is alluding to. If you have a battery that's not fully charged, you're depleting your range. You won't be able to go as far with UHF radios. If you're using a modem, obviously you're just going to go or fail. Here's the thing that a lot of people don't understand, or not understand, but don't use. I actually saw this at Trimble Dimensions a number of years ago. There's a guy that did a session on this for single base positioning. If you're using like a UHF radio, if you elevate your radio broadcast antenna, you're extending your range. He said if you double your height, you can get 40% more range for your real time. Sometimes that's important, at least it was for me. And you can't get it really, I mean, not more than 25 feet because then you need a low loss cable. You lose some signal by attenuation going down that cable. But if you can elevate your radio cable, you're using UHF radios, which a lot of us still do, and there's maybe areas, I don't know about C4G, but there's areas where I come from where you don't have cell coverage, that you need to do something. So you can do a repeater. What I mean by that is if you have work you have to do in a valley, and your base station's up here somewhere, and you go to the crest of the valley, and then you go down in it, you're going to lose contact with your radio. A repeater simply gives you another source of the signal, so you get to the repeater, and then the repeater down to you. And it'll work fine. So it might work conversely, of course, too. Check your fixed height once, at least, in each campaign. Your point wears, that could be 1 millimeter, 2 millimeters, 3 millimeters, I don't know. And then sometimes with a base station where it says 2.0 meters with a dowel that you slide through that hole, and you set your legs up, and you actually measure that height. You probably aren't going to have 2.00 meters. You're going to have several millimeters different. It's going to be a little bit more or less. That dowel, first of all, doesn't seat perfectly every time. But actually, we did that when we did the FBN reobs. Can't be too long-winded here. We had fixed height, like I said. It didn't collapse. And those checked very well, very well. But the ones that had the dowels checked several millimeters one way or the other. So just be aware of that. If you're trying to get good heights, why not start with the right values, even if it's only a few millimeters? Measure it once. It doesn't hurt. Frequencies in real-time single base, you have to make sure they're clear or you're going to get walked on by voice. Voice takes precedence over data. When the radio frequency overlaps or there's a harmonic or something like that, truckers on the interstate, if they're near their same frequency, they can walk over your data. Wait for and get a scanner for a clear channel. Of course, as soon as you go 5 miles away, that'll be busy again, but that's the way it goes. Here's the main thing here. When you're locating an important point, make sure that your communication, whether it's to the network or to your base station, is solid and continuous. Okay, if you have a flicker going on there, it introduces noise. I don't know why. It might have something to do with the latency of the data or something, getting backed up, I don't know. But it does seem to introduce noise into your solution if your communication is not solid and continuous. Of course, once you're done, you can throw it over your shoulder and go to the next point. But while you're locating the point, it should be continuous and solid. Firmware is important when you're doing a real-time network, especially. I've seen conditions where a person has had problems connecting to the network, and it was simply because he didn't have updated firmware. Manufacturers love that too, because that means you got to buy new firmware. So make sure your firmware is up to date. Conditions. This is where you want similar conditions from a base to rover if you have a single base. If you don't have similar conditions, what's happening is that your base station is sitting here and you're typing in a position for it. And it says, okay, I know where I am, and I see where the satellites are. They're telling me they're there, okay, and this is the range I should have to that satellite, but I don't. Okay, that means I have an error somewhere. That means that the weather or the ionosphere or something's doing that. So I'm going to send those corrections to the rover. So the rover's over here. And as long as it has the same conditions affecting that signal, okay. But if it doesn't, then it's going to apply those same corrections for a bogus condition, and you're going to get an error. It depends how much of an error, but it could be as much as to prevent you from getting a fixed solution. Just saying. And that depends, too, how far away you are, how the conditions change. So you want homogeneous conditions at the rover and the base. Obviously, watch out for multipath. It doesn't hurt to plan a little bit to make sure there's a time of the day when you're only going to have 6 satellites or something if you're just using GPS. So there could be a downtime of the day. Constraints. Do you want to localize to your project site? That's more of an important question here than it is in Maryland. You know, if you do want to, what do you have at your site that's truth? Maybe you have a couple monuments that have been legacy monuments that you don't care if they're 2/10 out. They're still truth. They're truth. Well, you can localize vertically to them for a 2-point calibration. You hold one as vertical. You adjust all your verticals to it and check the other one, make sure it works. And you have to have trust in those too, obviously. But you could do that. If you have a situation where you have 4 monuments producing a rectangle, you can do a nice horizontal adjustment and vertical adjustment. That's the ideal, to produce a rectangle. simply because if you have 3 on one side and 1 on the other, it can do a hinge and still adjust to that point if you type in the wrong value, which actually happened to us. So you want a rectangle the best way you can to localize to a site. Also, this is a great way of seeing any outliers in your control, because you're asking it to fit together. Does a least squares adjustment to those values? And if there's any outliers, it'll show you that. It'll show you the residuals from that adjustment. Yes, you can do relative positioning. Here's an old TGO calibration using known points. And what you get the adjusted value and the published and all that. And you can look at the residuals and see if any point sticks out as not being, comparable or of good quality. I think we talked about that. If you can do autonomous positioning with real time if you enter in the right coordinate for the base station later. So if you're out at a site and you say, oh man, I forgot that data sheet. I don't have it. Okay, well just set your point up, do an autonomous position, do your real-time positioning, then back in the software or back in the data collector, you can type in the good value for your base station, and because you're only producing vectors, differences in x, y, z, from your base station to your point of interest, it can just simply shift those 3D vectors over to where they should be. There's no real scale factor or rotation factor to worry about there. Okay, so in a local project, you can use autonomous position and enter the good position later, which most of us probably know that. Yeah, you type in a bad coordinate, everything you do from your base station will be wrong. Fortunately, you could correct it if you know you did it. Collection, the big one. Always check a point at the beginning of your session for real-time positioning. I don't care whether you're using a network or your own base station. There are too many ways to make blunders, especially with your own base station, than I can think of. And you want to make sure that you check just to be sure. I don't care if it's a topo point, something you did yesterday, whatever you got, the best thing you have. Go out and check it. Okay, yeah, all right, well, all right, fine. And then you go. Make sure you check a point. The elevation mask, I recommend 10 for real time. That's what I use. It eliminates the noisiest data, but it still allows most of the data in. If you need to, there's whether it's a Trimble QC1, QC2, or Leica, or whatever it may be, make sure that you're setting that data that gives you the covariance matrices on, and all that is producing an error ellipse, if you will. So back in the software, if you did more than one location, you can actually tweak your location if you have that set on. Download your data, your post-campaign real-time work can be tweaked if you have a redundant location. Just saying. Know that what you're looking at your data collector, not always, depends on the brand, could be 68% confidence, horizontal, vertical, RMS. So understand that we want to work with 95% confidence, at least I do. That means you double what you're looking at. Okay? No, I can't say that. Things change. It's, to my knowledge, a lot of equipment only gives 68% confidence displayed. Not positive about everything. If you're locating an important point, aside from redundancy, which we have to have on important points, and by redundancy I mean you come back to it later, not you dump your antenna and get another location on it. You want to blunder check that way though. Go about 100 feet away, and whatever you have to do to turn off the satellites, dump your antenna, whatever you have to do to reinitialize, do so. Go back to your point and get another location and just see how it compares. Does it compare good enough to what you want? If you want 2 centimeters, does it compare 2 centimeters or better? Okay. So that's a blunder check. It's not redundancy, it's a blunder check. There's no independent observation there, using the same satellites, the same conditions. You know, you want different conditions, different satellites. Multipath we talked about. Beware multipath. That's multipath. There's a story there, but I won't get into it now. This is just what NGS did to prove that redundancy is good if you use different satellites. Now that was, you know, probably 17 years ago. So I don't know if it's still true or not. There's a study by Newcastle in New England, University of Newcastle on Tyne. They're using a real-time network, but under certain conditions. I have an argument with that. I'm saying use it staggered by 4 hours. This is my boss, actually, now. We're out in the woods in southern Maryland, and we wanted to check something. We knew we weren't going to get a great position, but we said, let's just do it anyway. So he had the rover there, and he put it on this monument, and he had a 700ths precision. He said, well, you know, we can deal with that, okay. And he, you know, went over and then came back and got another shot, and it was a 10th. And he said, okay. Well, it was 6,500ths out. Here's the why. It was a long initialization time in the trees. Friends, don't let friends RTK under canopy. I'm sorry. I'm sorry. It's still true. It may not be true forever, but as far as I'm concerned, it's still true. Beware long initialization times. If it's sitting there and trying to figure out how many damn cycles are there from that satellite, you know, and sitting there and figuring, and finally says, got it, fixed. Beware, okay? Confidence, well, redundancy, check a known point, know what accuracy you need. So you know what accuracy you're getting. And then you can say, that's not good enough, or that's better than I need. So that makes it a lot easier if you know what you need. You want to average redundant locations. If you're within a calibration where you localize to a site and you have a base station, make sure that your base station aligns to the nearest calibration point to the accuracy you need. Make sure your base station aligns to this calibration point to 2 centimeters or better at 95% confidence if that's what you want. Yeah. Another thing too with GLONASS, very fast. Okay, GLONASS has ground monitoring stations, but they're trying to build out. But up to now, they've been all in Russia. That means when the satellite goes overhead, yeah, okay, oh, that's it, and then it goes over the horizon. That's it, until it comes around again. The U.S. has 6 or so, well, more than that, monitoring stations. And they have at least 2 of them observing each satellite all the time. So you can have a little bit more confidence in what we have than the GLONASS system. Sometimes it gets funky, all right? If you have trouble initializing and you're using GLONASS, turn it off and just do GPS. If you're having noisy solutions, turn it off and just use GPS, if you can. And you can compare each way, you know. But just to recommend it if you have problems with GLONASS. And you're using GLONASS. You can use inclinometers, you can use laser rangefinders for wetlands or something, come out in the open, where you can get a shot, laser range into the edge of trees. Automatically puts a position there. Snow and rain doesn't matter. Power transmission lines, sometimes it matters, sometimes it doesn't. Depends. I think it depends on how much current's going through the line. I've had conditions where you can work under it with no problem. I've had conditions where you couldn't communicate with the base. So it's kind of like, you know, you have to see what's happening at your site. We talked about tree canopy. You can look at a bunch of stuff in the office. You can't change too much, but you can look at it. Slope distance, horizontal precision, vertical precision, PDOT, number of measurements, satellites, that sort of thing. The antenna height, the XYZ vector, the northeast up components, and the azimuth and distance. Metadata is important with real time to keep track of what you're doing. Have a log. You can create a log and give it to your practitioners as it go out. There's a summary. I think we talked about most of that. You guys are pretty familiar with most of this stuff. And here is the 4 cardinal rules. Communication strong and continuous for important points. Always get a check shot before you begin work. Always get redundancy for important points, always. And be aware of multipath. Those are the 4 things to do to make sure you have confidence with your real-time work. Know what truth is for your project. This is the key. Use C for G, RTN as the truth whenever possible. That may not be true. I had several slides for what we already talked about recommending we do at the real-time network sites. That is, using the XGeoid 14B model. Okay, so I'm sorry. It was too much information for the time. You guys were very patient. I appreciate that. We're going to take a break, I hope, and then we're going to come back and do a panel session. Any questions or comments, Rotten Tomatoes, bring them with you, and we can talk about it till at least 4 anyway. Thank you.